This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on partial fraction setups. How do we set up problems using the method of partial fraction expansion? I want to take a look at a fraction, 5/6, and we're focusing on the denominator of 6. There are two factors in that denominator, 2 times 3, and they are distinct. They are different. And I want you to notice that 5/6 can be written as 1/2 plus 1/3. The method of partial fractions takes a large algebraic fraction and writes it as a sum of two individual fractions. And those two individual fractions are easier for us to integrate. That's our process. So we need to see what types of fractions we can get that are going to have a denominator of 6. If I add two fractions of denominator 3, the result will be denominator 3. If I add two fractions with denominator 2, the result would be denominator 2. But if I have a fraction with denominator 2 and another fraction with denominator 3, that's going to give us a fraction with denominator 6. That's our idea. Similarly, 13/15, we look at 15, distinct linear factors. 3 is a factor, 5 is a factor, they are different. If I want to come up with a fraction with a denominator of 15 using one denominator of 3 and another denominator of 5, will do that. So we have taken this 13/15 and broken it up into a sum of two fractions with differing denominators. That, in essence, is our process for doing partial fraction expansion. And this is how it works. So if we have 5 over 2 times 3, we're going to want to find out what would A be for A over 2, what would B be for B over 3. We have a fraction of each denominator. Same thing for 13/15, some fraction over 3 plus some fraction over 5. Now we know A in this case is 1, B is 1. We know in this case A is 2 and B is 1. But when we use the method of partial fraction expansion, we're going to do some algebra to find out what A and B are. And I encourage you to look at my videos that talk about that process. So here I have 2x minus 7 over x minus 4 times x plus 5. X minus 4 is a factor in the denominator. X plus 5 is a factor in the denominator. They are distinct. They are different. So I can come up with some fraction over x minus 4 plus some fraction over x plus 5. That would equal 2x minus 7. In our process there, a times x plus 5 plus b times x minus 4 over x minus 4 times x plus 5 equals this. And then we do some algebra to find a and b. Similarly, if I have three distinct factors here, x minus 2, x plus 3, and x minus 7. Notice this is order 3, x cubed downstairs, and the numerator has degree less than that, so the highest it could be, at least to begin this process, is order 2. Similarly, this one is order 2 downstairs, order 1 upstairs. Order 2, x squared downstairs, order 1, highest power is x upstairs. So, distinct linear factors in this example. I'm going to need a over x minus 2 plus b over x plus 3 plus c over x minus 7. And then we need to do algebra to solve for that. Solve for a, b, and c. We would build common denominators to do that process. So that's distinct linear factors. Our next example is going to be for repeated linear factors. And the arithmetic fraction we're going to start with here is 23 over 12. 12 is 4 times 3, or 2 squared times 3. So we have a repeated factor in the denominator. We want to think about the kinds of fractions we could build to get 23/12 as the result. So indeed, 3 is there once, but 2 is a repeated factor. And just looking at our example, I could break 23 into 8 plus 6 plus 9, 8/12 plus 6/12 plus 9/12. So of course, if I add three fractions with a denominator of 12, the result is a denominator of 12. But we want to build fractions with these simpler versions with 2's and 3's. And if I reduce this, you'll notice 8/12 plus 6/12 plus 9/12 becomes 2/3 plus 1/2 plus 3/4. So if I have fractions with a denominator of 3, 2, and 4, the common denominator is 12. If I had fractions with denominators 3, 2, and 2, which is what a lot of students want to do, denominators of 3, 2, and 2 would give us a common denominator of 6. So 3 and 2 is not enough. 3 and 4 is not really enough either, because I certainly could have a fraction with a reduced version of 4, i.e. 2/4 becomes 1/2, or 6/12 becomes 1/2. So if I want to build 12, I could have denominators of 3, 2, and 4, or 3, 2, and 2 squared. So this is what we have. 23/12 is 2/3 plus 1/2 plus 3/4. Or 2/3 plus 1/2 plus 3 over 2 squared. And if I want to build my partial fraction expansion, it'll be something over 3 plus something over 2 plus something over 2 squared. That'll be our idea. We're going to extend from this model to our repeated linear factors. So in this case, we have x minus 3 there once, but x plus 7 squared. X plus 7 is there 2 times. So I'm going to need something over x minus 3 and something over x plus 7. That will not be enough. If I have x minus 3 and x plus 7 in my denominators, I would not get this as the common denominator. I also need x plus 7 squared if I'm going to get this as a common denominator. Hence a over x minus 3 plus b over x plus 7 plus c over x plus 7 squared. And then we go through an arduous process of solving for a, b, and c. But this is our setup. Another example I have here, notice again, order 3 downstairs, order 2 upstairs. Here we have order 4, x cubed x to the first order 4 upstairs, order 3 upstairs. Order 3 is the highest order we could have in the numerator to do our standard approach of partial fractions. You could have something as simple as 1 upstairs, and the process still works. X plus 1 is there one time. I need a over x plus 1. But what about the x minus 5 cubed? Well, I need something over x minus 5, something else over x minus 5 squared, and something still different over x minus 5 cubed. Notice, if I add those 4 algebraic fractions together, what is the least common denominator? It would be x plus 1 over x minus 5 cubed. So there are 4 pieces we'd have to find here, and the algebra would get unpleasant, but that's how we would set that thing up to begin with. For repeated linear factors. So in the first example here, x plus 7 squared is in the denominator, so I need x plus 7 and x plus 7 squared. Here I have x plus 5 cubed. I need x minus 5 cubed. I need x minus 5 squared, and x minus 5 cubed. All right, the next example I have is for an irreducible quadratic factor. X squared plus 9, a sum of 2 squares, does not factor. So how do we handle that situation? Think about our degrees. The degree of the bottom is 3, x squared times x, x cubed. Degree of the top is 2, x squared is the highest power. That is workable for us in the world of partial fraction expansion. We want the degree of the numerator to be less than the degree of the denominator. Now, x plus 4 is a linear factor. It's there once, so we will need to have a over x plus 4. What about x squared plus 9? b over x squared plus 9 is not enough, because x squared plus 9 is a quadratic factor. What has to go on top is something that is 1 degree less than that. I need a linear factor up there, something whose highest power is x. So the numerator above the x squared plus 9 will be bx plus c. When you see an irreducible quadratic factor, something of the form bx plus c needs to go on top. A first order polynomial on top of a second order polynomial. And then the usual strategy, a times x squared plus 9 plus bx plus c times x plus 4 over x plus 4 times x squared plus 9 equals this entire fraction. And we go through the algebra. Our next case, order 4 downstairs, x squared xx. Order 4 downstairs, order 3 upstairs. The highest power we can have on top is 1 less than the highest power at the bottom. X minus 6 is there once, so I need a over x minus 6. X plus 2 is there once, I need b over x plus 2. Now what about the x squared minus 11x plus 1? What's happening here? That is a quadratic factor that does not break down into linear factors. I cannot factor it over the rational numbers, over the real numbers, probably. So we're not going to try to factor that. We're just going to recognize that's order 2. So what has to go on top is an order 1 polynomial. It's got to be bx plus c over x squared plus 11x plus 1. Except not bx plus c, we used b before. A and b are used. So an order 1 polynomial would be of the form cx plus d over x squared plus 11x plus 1. And this is what we would have to do. We'd have to solve for a, b, c, and d. before we would actually go ahead and complete the integral. Let's look at one more problem. Downstairs, x minus 7, 2x minus 5 squared, x squared plus 25, x squared, x. Fifth power downstairs. I could have as much as the fourth power upstairs. Or something as simple as 1 could be upstairs as well. X minus 7 is my first factor downstairs. It is unique. There is no second version of x minus 7, so a over x minus 7 is where I'm going to start. Now I have 2x minus 5 squared. I will need b over 2x minus 5 for one of those. But then I will need another thing over 2x minus 5 squared. So it'll be c over 2x minus 5 squared. And then the last thing we have here is x squared plus 25. That is a sum of two perfect squares. It does not reduce. I need a first order polynomial on top, something x plus something. Since we've used a, b, and c, we will go with dx plus e over x squared plus 25. It would be a very, very challenging thing to do to solve for a, b, c, d, and e, but that's what you would have to do before you would go on and try to solve this using the technique of partial fraction expansion. And that will conclude this lesson.